Alright, let's begin. So for the engine, we had to implement AABBs. So as you can see here, AABBs, now they have collision with B spheres here. And if I were to move over to the axis, we can see we have collision with the axes as well. And we can also see that the box always stays aligned with the frigate. Leaks. So setting the collider model now takes in a collision type enum. So if it's a B sphere, we create a B sphere. Otherwise, we create an AABB, which means the collision volume is now a collision volume pointer rather than a B sphere pointer. Um, Whenever we test for either a collision self or a collision pair, we now call except intersect on the two generic collision volumes rather than specifically B sphere to B sphere. So if I go to B sphere, except intersect with the generic collision volume, as well as a visit for B spheres and AABBs. So whenever we accept the intersection, we force this unknown collision volume to do its visit intersect on a B sphere. That way, that collision volume will know which intersection test we need to do. When the B sphere is that other, if it's also another B sphere, we got B sphere to B sphere collision. Otherwise, if it's an AABB, we got B sphere to AABB collision. AABBs, we have a similar setup for the visitor pattern where we force the other to do its own visit intersect on the AABB. If that AABB is the other and it needs to collide with the B sphere, we got B sphere to AABB collision. Otherwise, if it's an AABB, we have AABB to AABB collision. For computing the data, we get the first point in the model's point list. We set the minimum and maximum to be that, and then we iterate through all the remaining points in the list, and we find the minimum min and the maximum max for each of the coordinate values, and we make the min and max using those new values. For the math tools, B-sphere to AABB collision, we clamp the B-sphere center to the AABB, get the vector between the clamp point and the center of the B-sphere. If the dot product of that new vector is less than the radii squared, there's a collision. And for AABB to AABB, we have to get the min and max of both AABBs and check for overlap on all three axes. If there's overlap on all three axes, there's a collision. If any of them has no overlap, then there is no collision. For the tank demo, I did not succeed in my work this week for this one, unfortunately. My goal is to try and have a HUD indicator for the closest tank. So as you can see here, I have a big sphere that points to the closest tank. But you can also see I have this exclamation point that's snapping all over the place. My goal is to try and have it be where this sphere is, but it's currently not set up properly. So for the calculating of that sphere's position, we have a get closest tank world function now. It will get the first active tank in any of the lists. Whatever the first active tank is, that's now our new distance to player, which is that tank's position minus the blue tank's position, and then we use max square for it. And then we set the tank pointer to be that closest tank. After that, we iterate through all the remaining active tanks, and if we find a new shortest distance to player using the max square formula here, then we update the distance to player and also the closest tank pointer. And once we go through all that, we return the world of that closest tank. So in this tank tracker, we try and get that closest tank world. The sphere's world is that closest tank's world with an offset and a bigger scale to make it easier to see. And then I try and clamp convert the 3D point of that world into the 2D space, which looks like this. So what I have right now is screen position is the point in 3D space. We get the view matrix. We extract the cam position from that world view matrix because we're going to be just transposing it to transpose the rotation. So once we transpose the rotation, we multiply that camera position by the new rotation values, multiply it by -1, and then insert it back into our world to view matrix. After that, we update the screen point by that world to view matrix. Next step is multiplying the screen position by the projection matrix of the camera, which will give us a homogeneous coordinate that we have to return back by dividing all of the coordinate values by W. We recompute the screen position with those new values, and then we use the NDC point, which we get based on the window width and height, as well as the Z depth, which is 1 for this. And that gives us a screen position with 0, 0 in the upper left. Since I want 0, 0 in the lower left, as that's what we've been using as a standard, I just do a bit of shenanigans to change that. That's it for that. The last implementation is the buttons. So just to quickly go over them, there are 3 different types of buttons. One is a push button, which we'll call the push and then immediately release itself. There's a hold button which will constantly call push while the mouse is down and then release it regardless of wherever the mouse is. And then we have radio buttons which will call one press, and then when a new press is called, it will call release. So as you can see here, we have that working fine and no leaks. So so all buttons have two different graphic objects attached to them: a button down and a button up state. So whenever a button is pushed or released, it will change it to the appropriate graphic object for its rendering. Radio buttons also have a sprite string that is attached to them to show what each of the options are. All radio buttons are attached to a radio button group. So whenever a user creates one, they can submit it to the screen with a number of how many radio buttons they want attached to it and what mouse button they care about. This will say what the active count is, request its register to be drawable, and request the registry for inputs. If the user wishes to update the text for any of the radio buttons, they can pass in the enum associated with that radio button, and then the sprite font they want it to be rendered in, as well as the sprite string. This will update the text value to be based on that. We can set the position of the radio button group, which is used to update all the radio buttons for the rendering. So whenever we render a radio button, it's similar to how we render the sprite strings, except instead of increasing the x by the by the given glyph's width, we decrement the y value by the height of the button. And then for testing the mouse press states for it, we loop through all the current active buttons until either we reach the end or we find a button that we've pushed. We get the width and height of each button, we clamp down on that mouse position, and if we have a successful collision there, we release the last button that was pushed and then push the new button. So these values will go through the attorney to the associated radio button, which will update the index for them. This index is used in a switch statement so that we know which of the released and which of the pushes that we want to use, which is similar to how we have the alarms implemented. And then whenever we submit AABBs, we deregister everything to it. So the test radio button, you see here we submit the entry, set the position, and then update all the options for it. And then we have the test code here. For the push button, once again, they have the up and down state. I also have a bit of a strategy pattern here so that it knows when it needs to release itself in the next frame. Mouse press and release is the same thing as radio buttons, except for this one it has an engine push and release rather than calling push and release directly. So in the engine push, this is where we update the button state, as well as saying that it can be released in the update state. And then when it calls release, we just release it. So for the push button, we have the engine release, which is called by the release me call back over here. And then for the test button, we set the position. For the held button, it is similar to what we had for the push button, except we use mouse down instead of mouse press. And while the mouse is pressed, we have a button push flag. So once the mouse is pressed down in the right position, that flag is set to true. So even if the mouse is moved off the button because the mouse is still held down, then we have a push still. And then on mouse release, if it's the right mouse button and that flag was set to true, we call the engine release, which will update the state to be up and then set the flag to be false. And then it's the user release. So for the test held button, same thing over here, except I also added the setting of the scale so that we can show that scale factor can be affected. And that's it.